Hello, and welcome to my project showcase presentation. I have developed an automated PCB inspector for my project, and in this presentation, I will take you through the different steps of the project. To start off with, I will cover my inspiration for this project and why I chose to make it. I will cover the objectives of this, the outline of what it must achieve, along with the method and results, and the further applications for it. I had the initial thought for this from my time working on my placement year. The majority of the work was spent inspecting printed circuit boards, PCBs. This was a time-consuming effort and was often done after production, which resulted in wasted time and a lot of inefficiencies in production. Two key issues were at play: a lack of pre-production inspection and a lack of automation in inspection. With this in mind, and a lack of affordable options for manufacturing, I started research into developing my own system. For this project, I wanted to develop something that would be easily able to be used with any USB camera. I wanted it to be able to tell the difference between a good and a bad board, identify missing components, and to identify the fault by name. For this to be a reliable product that would surpass existing systems, it would need to be able to operate with consistent accuracy at consistently higher speed, whilst working with misaligned boards. This is something that was often an issue with the existing systems, that they would be unable to handle any deviation in angle or size of an image, and they would require a nest for inspection. These systems would also require very consistent lighting, which would have issues if ambient light was able to penetrate and reach the product. Lastly, I wanted a product that would be reusable with only a few minor tweaks, something that would be relatively simple to set up. So when starting out with this project, these were the key points that I kept in mind. The main steps of the project have been outlined on this slide. These are the key steps that the program runs through. The system starts by taking a photo, using the camera. After this, the images are treated for brightness, alignment and scale, so that they are in the same position as the reference image. After the image treatment, the treated image is then subtracted from the reference, and the resultant difference is then dilated and eroded to remove noise. After this, the difference is then compared to the preset coordinate locations for components. This then outputs the component name for the component inside of the coordinates. Prior to running, a coordinates file must be generated using the built-in program. From the outline, I have 5 main sections for this program. I will go through the general theory behind each section alongside with some examples of the code and the specifics that make this work. Images are captured using the video capture feature in OpenCV. The image is then read, stored locally, and saved to the file path under capture. The captured images are then used as input images if the user camera feature is turned on. This is the code that I've used for the image capture. I've also added an additional if statement that will output an error if the camera is not connected. This is intended to help with fault finding if any errors occur. Using a USB webcam, this is the image that I was able to capture, and this was the reference image that I used throughout this project. For the image realignment, I used the system called homography. Homography represents how two images on the same plane are related. A homography matrix represents the relationship between the two images and can be used to adjust one of the images to match the reference. This effectively adjusts the image and treats it for differentiation in orientation and scale. To calculate homography, we first need to identify many similar feature points between the two images. For this, there are a lot of methods such as SIFT, SURF, KASE, AKASE, ORB, and BRISC. I've chosen to use ORB feature detection for this project as it is a free and efficient alternative to SIFT and SURF and runs with a lower computational cost. This means that using it over SIFT or SURF will allow it to run much faster, without sacrificing too much accuracy. Kaze and Akaze featured additional systems that were not needed during this project and would require higher computational power. These are systems that I would look into using if I were to develop this project further. As for Brisk, when researching, Orb presented better results in almost all aspects of feature detection. Here is the demonstration of the code that I'm using. The first step is to convert the color for each image to a grayscale. Then we make a vector to store all of the key points that will be detected. After this, we create two matrices for storing the descriptors of the input and reference images. We then use Orb feature detection to identify all of the key points and descriptors for both images. After this, we use another vector to match the descriptors for each image. We then sort matches by the highest score to rank them in accuracy. The next step is to remove any bad matches. To do this, we have a set good match percentages, which we multiply by the size of matches. We then erase matches that are not between the highest ranking and the good match percent. After this, we draw the matches on the image. Next, we create a vector which stores the locations of all of the good points. After this, we iterate through each match and update positions of the points. We then use these to calculate the homography matrix, and using the homography matrix, we use the warp perspective function to adjust the input image to match the same size and alignment of the reference. Then we store the output images. This image shows the identified matches from both the input and reference images. This image shows the realigned image next to the reference image. These are nearly perfectly aligned. For setting up a difference detector, we first need to treat the image for the effects of brightness to allow for mild fluctuations in light to not affect the usage of the system. To do this, I used a color filter to set a minimum value that will remove the darkest areas and a maximum value to reduce glare and avoid detecting the background material. Next, we use the absolute difference function, which will subtract the reference and the corrected image. After this, it is eroded and dilated, which eliminates noise and helps to remove false errors. Here is the code that I have used. In this, we first check if the reference or input matrix is empty. This helps with fault finding if any issues arise. Then I use color thresholding, which uses the in-range function to save all of the colors that are within the lower and the upper bounds, and eliminate the rest. These bounds are set with relevance to the application, and must be determined prior to usage. After this, I'll calculate the absolute difference, which subtracts the input from the reference, but removes negative values. After that, I set the brush size and the brush element. I then set the color range to search through. After that, I use the erode and dilate tool with the brush element and size to remove noise. I then create a black matrix and set the error on the black image in red and save the result. This is the resultant difference from the two images on the output that's been saved. In this section, I will review how I've set up the user configuration for products. To do this, users simply need to update the file path with their new product and update the variables in the switch cases to include the new product. After this, users only need to run through the built-in program which reads mouse inputs and allows users to highlight and store the coordinates and name for the component. Here is some of the code that I've used for user configuration. The first structure is a structure that holds the component data and selection mode. The next portion is the callback function, which detects mouse inputs. If the left button is pressed, then it stores the initial coordinates and sets the mode to select. If the left button is released, it stores the final coordinates and sets the mode to label. If the right button is pressed, it cancels the selection. Otherwise, if the selection mode is true, the mouse will update the coordinates as it moves according to the mouse positions. Here is the next step of the code. In this we have the drawboxes function, which sets up the drawing area for the user by calling the mouse callback function with reference to the drawing window. The next step runs through a selection case that saves the coordinates locations to the structure. After this, the program uses the label case, which uses getLine to allow users to enter the name for a component. After that, the user must have entered all of the component names. They can save and write the coordinates and component names by pressing Escape, which saves all of the local arrays into an XML file, after which each loop the system updates the image drawing window with the previously drawn rectangles. This code shows the case for changing the user path to the selected product to use. And this shows the user drawing window and the saved coordinates file for that session. In this section, I show how we use the coordinates file to identify faulty components and how the use of them helps to exclude noise from the system. In this section, I have a struct similar to the one given in user configuration. This is used for storing components locally after reading. Next is a boolean that detects if a coordinate lays within the component selection. When this code is run, it will start by opening the coordinates file and converting its contents into a locally stored vector. The detected difference is then open and the program iterates through each component, creating a rectangle and checking for any points that are not black within that rectangle. If any points are found, the system outputs the name of the faulty component and sets that an error has been detected and exits the loop for that component. If no faults have been detected, the system outputs that no faults have been found. This slide shows the output of the system. This has detected 3 faults with components, and these are output in the user interface by their stored names. As seen in the previous sections, we can note that the system has been accurate to the known faults with the PCBs used for testing. We have tested this with different scales, orientations for the boards, and have found that it consistently corrects these issues and functions as expected. As for brightness, I've tested this with 4 brightness levels. The system is able to handle this with high, medium, and low level light, but struggles when using solely ambient light. However, this system would be set up in a controlled environment, and this is considered an acceptable issue. With regards to timing, at the start of this project, I found that on average it could take 30 seconds for a simple fault and up to 10 minutes for a more difficult fault when inspecting manually with a microscope. This system has proven to work reliably with the PCBs at a fastest time of 1 to 2 seconds or less, and at the slowest time of 6 seconds with very large images. In terms of the future for this project, further advancements that I have considered to improve this project are setting it up in a manufacturing test equipment rig to improve how the project can be implemented, using additional support for the user interface with systems such as Qt, or setting up as part of a LabVIEW environment would allow the system to function easier for users. Additionally, setting up a more advanced product setup that would generate file paths and reference images automatically would allow users to easily add new products with fewer steps. As discussed during my research, feature detectors such as Kaze and Akaze would be suitable replacements for Orb, which would increase the accuracy of realignment as well as minimizing the effects of brightness. Following on from that, further systems for maximizing brightness tolerance could be researched and implemented. At the moment, I've tested methods using histogram equalization and HSV adjustments, but have found that colour thresholding is the most consistently accurate for this application. Thank you for your time.